Hi class, I hope that you've learned a lot today about integrated rate laws and how to determine whether something is zero order, first order, or second order just by looking at their graphs of time versus concentration, ln of concentration, or 1 over concentration. I want to just hit one more topic very briefly. Integrated rate law determination with 2 or more reactants. So sometimes we have 2 reactants that are involved, and it's kind of hard to isolate one reactant. So we've got this method that we call flooding that we use. This is a strategy of flooding the reaction mixture with one reactant. It allows us to isolate the effect of the other reactant on the change in the reaction rate. So the big problem that kinetic studies has is that every reactant concentration actually changes at the same time as the reaction proceeds. So measuring the rate of change of one reactant independent of the range of the other reactant requires a little bit of a trick, and we're going to talk about that trick. So imagine that we have a reaction between 2 reactants. Let's call it A plus B yields product. We'd expect the rate law to be rate equals K times A to the N times B to the M. Concentration of A to the N times concentration of B to the M. If we want to isolate the effect of changing the concentration of reactant A, I just want to focus on reactant A and understand its kinetics while keeping the concentration of B pretty much the same throughout the time of the reaction. We'll need to devise a way that the concentration of B won't be changed significantly. So it won't be used up significantly when A reacts to become products. Basically what we're going to do is make A the limiting reactant by a huge factor intentionally. So let's imagine doing the reaction with a large excess, 100 times more of reactant B. So that reactant A is obviously the limiting reagent throughout the course of the reaction. So this diagram, and by the way, we're going to talk about ice tables later. This is kind of a preview of something we'll do when we get to equilibrium. But we've got our initial amount. We've got X. We're just calling the amount of A that we have X. And B, the other reactant, we have 100 times as much, so it's 100X. Well, as the reaction occurs, if this is a 1-to-1 ratio, as the reaction occurs, that X is going to be used up. It's the limiting reactant, so it'll be used up, and the final amount of X will be 0. So it went from X to being 0. We got rid of all of that. Well, if A is the limiting reactant, that means I'm going to use the same amount of B because it's a 1-to-1 ratio. So 100X minus X, I'm just removing the same amount, is just 99X. And then we got X as the amount of products that we made. From the above limiting reactant calculation, we can see that we used up only about 1% of the amount of B that we started with, while we used up all of the A that we started with. So we should be able to assume that the concentration of B has not really changed very much. We had 100X in a certain amount of a solution. We ended up with 99X in that same amount of solution. Not a big change in concentration. By evaluating how concentration of A changes with time, the reaction order with respect to A can now be determined. All right, how would the experiment change to evaluate the reaction in order with respect to B? So think about that for a minute. How would we do this differently if we were really wanting to evaluate B for its kinetics? I hope you identified that the best way to do that would be to start with X as our amount of B and 100x as the amount of A. We would have 100 times as much A as B, so that we could evaluate B as our limiting reactant in order to evaluate its kinetics. So this is not necessarily something that is heavily assessed on the next test, but I wanted to cover the topic with you in case something along these lines does come up as a concept or a topic that's discussed in an AP question, and also to further prepare you for college.